Okay, I think we can start. Our next speaker is Shota, who will talk about topics on QFT and AdS for 3 lectures.
All right, so thank you for introduction and thank you for invitation. So yes, today tomorrow and Friday, I'm going to talk about 3 topics on QFT and AdS. So the idea is that 3 lectures are mutually related, but at the same time independent. So if you miss one lecture, you will be able to follow other lectures still. So these are 3 topics that I'm going to discuss, and I put some references. It's not obviously like a exhaustive reference. It's just my papers, but but there you can also find relevant references. Of course, along the way, I also mentioned several important references. But in case you want to see what's going on and what are other references, you can also go to those papers and then see it. So the first topic that I'm going to talk about, which is the main subject of today, is a flat space limit of AdS. I'm not going to talk about gravitational amplitudes in AdS. My main focus today is about consider quantum field theory in AdS, especially massive quantum field theory, and understand how the correlation functions on the boundary that you define on the boundary of AdS becomes scattering amplitudes in AdS. And in the second lecture, I'm going to talk about some application of QFT in AdS, why it's important, why it's useful, especially in understanding the emergence of mass gap and confinement. And I should mention that today, this morning in arXiv, there was a very nice, beautiful paper by one of the authors there, Ricardo and Fabiana, Lorenzo and Marco Cerrone. So I'm also going to mention that in the second lecture. And in the third lecture, I'm going to point out some additional subtlety about taking the flat space limit and its relation to non-invariable symmetry. Okay, so let's start. So let me start with the introduction. So as a section 0, let me just give you some motivation why studying QFT in AdS is interesting and what we can hope to learn from it. So the basic setup is, as I said, I consider AdS space. So AdS space topologically looks like a cylinder with the interior, and then a boundary is where normally CFT lives. So what I'm going to do today is to put massive QFT in AdS, okay? And then, so AdS has some size, so let's denote it R-AdS. So very roughly speaking, the expectation is that if you send R to very large, keeping the mass of the theory or coupling constant of the theory fixed, then you should be able to recover some physics in flat space. Okay. Well, this is just like an expectation coming from the geometry. Because if you take the large radius limit of AdS, the geometry becomes flat space. But more precisely, the kind of thing that we want to understand is that here on the AdS spacetime, the natural observable that you want to consider is a correlation function of the operator that you place inside at the boundary. So this is the boundary correlator. And then this boundary correlator emits some particle inside AdS, and then they interact. And the hope is that this 4-point function, for example, should somehow become some scattering amplitudes in AdS, in flat space, which depend on the Mandelstam variable. And so this is the goal of today is to okay. It's not the battery is going down. Okay, so to understand how this procedure works in detail. But before talking about that detailed subject, let me also give you why we should care about flat space limit of AdS. So the one thing I immediately need to point out is that QFT in AdS, especially the AdS space, gives you a very nice IR regulator of the quantum field theory. In particular, because of the AdS size, like IR divergence is cut off, and then you get some IR finite quantity. And in addition, AdS space has as many isometry as the flat space. So it has it's very symmetric space. And finally, as I already mentioned, it allows you to define some analog of the asymptotic observables, like which is basically boundary correlation functions. So, and I would say like probably maybe AdS might be the only spacetime which have all these features, all these three features. For example, if you want to just regulate the IR divergence and keeping the symmetry, you can also put the quantum field theory on SD, the d-dimensional quantum field theory on SD. So that is perfectly like a finite IR finite spacetime, and also like it has a large symmetry. But obviously, like in that spacetime, you cannot define the analog of the asymptotic observable. And if you just care about symmetry in asymptotic observables, then of course like you can also talk about flat space. But then like IR is not cut off. So if you consider asymptotic free theory, the long distance physics is very strongly coupled. And also like in some cases, there are also IR divergences. Okay. All right, so that's the one thing I wanted to point out. And another thing which is more related to the Bootstrap is that, as I said, if you consider QFT in AdS, you can consider boundary correlation functions, which basically have the same features as the usual conformal field theory correlation functions. And the only difference is that we don't have a stress tensor, because we don't have a graviton in the bulk. By the way, this is a little bit small, so let me just write it bigger. And the nice thing about this is that because it basically behaves like a conformal correlation function, there is a hope that like we can control its analytic property. We may be able to know more about its analytic property as compared to its flat space counterpart, which is S matrix. So analyticity is probably better understood, and of course, like that is thanks to the fact that in conformal field theory we have a OP expansion, and then OP converges at finite radius. So maybe using this, one might hope that we may be able to gain some insight into some non-perturbative analyticity of S matrices. In particular, this is like a very, very much open question for higher point amplitudes. Okay. So let me just a bit more kind of concrete about like what kind of question may be interesting to address or answer in this context. And so maybe one thing is that like in the past, like in the context of conformal field theory, people have developed analog of the Regge theory in the QFT, which we call conformal Regge theory. So this can be understood. It's basically the one-to-one correspondence with the Regge theory of the S matrix. But in CFT, we actually are in a better situation because those Regge poles that appears in the conformal Regge theory, we know where it comes from. It basically like so those like operators with well, analytically continued spin, we know that it comes from basically, you can also construct the object that's responsible for that, which is basically light ray operators. And I think it is probably fair to say that in the case of S matrix, we don't have such a detailed, precise understanding of what is the object which is giving rise to the regipoles, the polymerons, and then region. And maybe using the relation between a flat space and AdS, maybe we can learn a little bit more about what this object is. So this is kind of like one possible application which hasn't been explored. Maybe like I shouldn't flip the page so early.
Where will it be important for you? Why cannot do also a massless QFT? Or, well,
yeah, yeah, I think. So today I'm going to talk about the subtlety about taking the flat space limit. It kind of gets worse in the massless series, so that's why I'm going to avoid talking about it. But in principle, like there is a way to make progress. Okay. Right. So, and then maybe another thing which I recently learned is that people in CFT and also amplitudes recently are analyzing higher point amplitudes and correlators. So there is a lot of active activities about higher point bootstrap in CFT and also maybe amplitude as well. And furthermore, there are some attempts to generalize the conformal Regis theory for higher point amplitudes and the Regis theory. And in particular, if you want to generalize a conformal Regis theory or a Regis theory to higher point amplitudes or scattering higher point amplitudes or correlation functions, you often need to analytically continue not just spin, as in the analytically continue the quantum numbers which are not the usual spin that we talk about in the context of 4-point amplitudes. And then furthermore, like in some cases, especially if that quantum number corresponds to some kind of labels describing the tensor structures, and there is a conjecture that there is no dynamical pole in that quantum number. So there are some argument in the context of amplitudes, but it's not, as far as I understand, it's not fully rigorously proven. And furthermore, in the case of correlation function, it's not proven at all. There is no like a strong argument at all. Well, this is what I recently learned from Joao over there. So if you want to know more about it, like you can ask Joao. And so probably if you want to, for example, like show something like this, like establish some like a theorem of the absence of the dynamical pole, probably it's easier to first try it in the conformal field theory, and then like maybe try to understand what's going on in the case of amplitudes. Okay, so these are kind of like two things that might be interesting to explore, but of course like there are many more in the context of like analytic properties of scattering amplitudes and correlation functions. Okay. Now, let me also give you yet another motivation, which is more related to the second lecture. So the point I want to make is that the AdS space is a perfect space-time for analyzing asymptotically free series in AdS. So what is asymptotically free theory? Well, asymptotically free theory means that if you go to UV, the coupling is weak. If you go to the IR, coupling is large. Okay, that's one feature of asymptotically free theory. And normally, in flat space, if you consider, well, the many interesting physics comes from the strongly coupled physics because like, we are interested in low energy observables. But the nice thing about AdS that AdS size gives you a natural cutoff, the infrared cutoff. So in particular, if you consider very tiny AdS, then the coupling constant is actually very small. So this is like a weak coupling and a perturbative. So this is thanks to the feature of asymptotic freedom. But of course, like if you really want to understand the physics in flat space, we need to study this regime. And in this regime, of course, because of the asymptotic freedom, the coupling is very large. So now, so this is a flat space and a strong coupling. So now, you can ask what is going to happen in between. So this is a big question mark. And so there are like several, many people who are interested in this question and who analyze various different models. And then basically speaking, well, there are like two scenarios, the two situations. And in the first situation, there are situations in which like, one expects there is no phase transition. So this also depends on what kind of boundary condition you impose for the quantum field theory in AdS at the boundary of AdS. So this in particular, I'm going to explain a bit more in the next lecture. But for example, if you consider what's called Neumann boundary condition of Yang-Mills in AdS4, people believe that there is no phase transition between the weak coupling regime to the strong coupling regime. And the second scenario is, of course, there is the other one, which is there might be a phase transition. And then that is expected to happen in what's called Dirichlet boundary condition for Yang-Mills theory. Okay? And actually, both of these situations are quite interesting. And let me explain why. So let me first explain why the first one can be interesting. So the first one, basically, there is no phase transition between weak coupling to the strong coupling. And if that's the case, there is a chance that maybe we can understand some mass gap and confinement semi-classically. Because precisely because like we are in the same phase as in the flat space, which we know to exhibit confinement and mass gap. But we can analyze that theory at small AdS radius and then try to understand some qualitative feature. And I should mention that a similar idea was explored by various other people, and it's often called like an adiabatic continuity. And this idea was like, for example, discussed by Argyres and Unsal, Popitz, and others. So what people were saying, well, they didn't analyze QFT in AdS, but instead what they considered is like take Yang-Mills theory and then compactify one spatial direction. But if you just do the periodic boundary condition and compactify on a spatial circle and then take the spatial circle to very, very small, if you make it very small, again, there is some kind of like a IR cutoff, and then you can hope that you can study this system when this circle is very small. However, if you just do it naively, taking a periodic boundary condition, the small size regime is actually deconfined phase, which is not directly related to the confined phase in the flat space. However, they argue that like if you kind of like you introduce some twisted boundary condition, or if you introduce some adjoint fermions, you can actually make the small circle regime also confining. And there, they kind of try to understand the qualitative features of the confinement using the semi-classical analysis and using some relation with resurgence and also semi-classics. And then I want to point out that there is a chance that one can also do a similar analysis in quantum field theory in AdS. And in particular, quantum field theory in AdS can be actually better than just compactifying a small circle on a small circle and then putting a twisted boundary condition, because it preserves a lot of symmetry. And in addition, you can also hope to study it with Bootstrap. And here, maybe one can also explore the interplay with semi-classics or things like renormalons, and possibly resurgence. But I should say that this part, I'm not going to talk much about this in the lecture. And furthermore, more generally, this aspect, I would say, is not much explored yet. Okay. All right. So now, there is the other one, which is the scenario in which there is a transition. But that is, of course, also interesting because there is a chance that one can understand this. So in the case of Yang-Mills, this transition is precisely confinement-deconfinement transition. And then this is quite interesting because one can actually, this provides a setup in which one can potentially analyze a confinement-deconfinement transition using the Bootstrap. And in particular, whether one can, the first question you would ask is whether we can prove the existence of the phase transition using the Bootstrap, and if so, what can we learn about its properties? And regarding this, there was a nice paper I already mentioned. So there was a nice paper, so I want to write it explicitly. So the paper today by Ricardo in the audience, and then Fabiana, and Lorenzo Di Pietro, and Marco Cerrone. And I hope to explain some of the contents of this paper in the next lecture. Okay, so far so good. All right, so I guess I spent too much time probably than I expected. So now let's talk about the flat space limit of AdS. Okay, so let's see. So the goal of today in the remaining 30 minutes, or a little bit more than 30 minutes, is to understand how this 4-point function really becomes the S matrix. And so in particular, when and how this works. And so another thing is that, so sorry. So we expect that the 4-point function becomes S matrix if you take the RADS to be very large. But and then these two objects both satisfy the unitarity constraint. But the unitarity of the 4-point function looks like, okay, sorry. Basically translates to the fact that this C delta J is positive. So this is the unitarity of the 4-point function of the CFT, whereas the unitarity of the S matrix, 2 to 2 S matrix, is basically like S square, absolute value of S square is smaller than 1. And if you compare the two, then you can see one interesting difference. So on this side, the unitarity is basically a constraint on some object which is linear in the 4-point function. Whereas here, the unitarity, as in the way normally stated, is a linear and then non-linear in the quadratic constraint on the S matrix. So you can ask like how are they related, whether one implies the other, or like the other one is stronger than the other. So today I'm going to also explain that how this linear unitarity constraint actually implies the nonlinear unitarity constraint. And the third thing is that is there some map between, so if this works, then there should be a map between the cross ratio, which is governing this 4-point function, to the Mandelstam variable S and T. And I'm also going to present how to understand and how to relate these to invariants. Okay. All right. Any questions so far? So this is what we are hoping to achieve today in the remaining 35 minutes. So let's first talk about kinematics. By the way, is it too small or it's okay? All right. So as I said, again, let me just draw this picture. So like you consider this QFT in AdS, and then take the limit when our AdS is very large, keeping mass and coupling constant. Then you expect to get the flat space. So let me just first translate this into the CFT language. So in order to do that, I'm just going to use the familiar relation between the mass of the particle in AdS and the dimension of the operator at the boundary. Okay? And so this basically means that if you want to take this limit in which R is very large and then mass is held fixed, then the dimension of the operator that you get in the CFT side is all very, very large. And this basically means that in the QFT and AdS side, the Compton wavelengths of the particle is much, much smaller than the AdS radius. And because of that, you can treat it as some kind of classical particle. Moving along geodesics. Okay? So the emerging picture is that if you insert some operator at the boundary, like this, then it emits particle. But this particle, because of this condition, in the limit where our AdS is very large with M fixed, it basically travels along the geodesics. And then they meet at some point in space-time. This is supposed to be a single point. And then interact with each other when their Compton, when their wave function starts overlapping. So this picture basically kind of suggests that 4-point function in this limit should be given by the S matrix of the flat space, which governs the interaction here, times some leg factor, which basically is coming from some propagation along the geodesics. So in the rest of the lecture, I'm going to make this statement a bit more precise. But before doing what is the subtlety or whether this really works, discussing whether this really works, let me just immediately give you, yes.
These leg factors.
Could you go back to the previous? Oh, here you are. Okay.
Oh,
So
okay.
a couple questions. One being the massive geodesics in ADS never reached the conformal boundary. So what are we supposed to make of that?
It's a tunneling geodesics.
It's what?
Tunneling. It's a Euclidean geodesics. So you're talking about like if you consider Lorentzian
Okay.
ADS and then like the actual particle geodesics, it is true that it never reaches the boundary. But what you basically need to do is to kind of like let particle tunnel through this ADS wall, the potential wall. So that is kind of like a Euclidean geodesics.
Okay, so then I'm not sure how literally I should be taking this picture. These curves drawn here are not actually Lorentzian curves. They're...
That's, okay, yeah, so at this point, like, yeah, you can just take it as a schematic picture. I'm going to make it a little bit more precise at the end of my lecture today.
Okay, and then one other question, which is that this relationship between the mass and the conformal dimension, I'm used to seeing this for free fields in the bulk and generalized free fields on the boundary, but I'm not sure exactly how I should be interpreting this for interacting theories.
Right, so, but here, like, I'm thinking about, like, putting some QFT in ADS with Lagrangian description. So I'm basically using the free field dictionary. So, and then, like, and then, of course, like, they start interacting, which means that this dimension gets shifted because of the interaction.
I see, okay, so this would be some weakly interacting theory then at this point.
Right, at this point, yes. But, yeah.
Okay, thanks.
I wanted to ask just kind of a naive question. Here. Yeah. Here.
Simple mechanics.
Thank you. Okay, so if I have a very slow particle, so I think you also have to care about the Broglie wavelength, right? If you have a very slow particle, it will be extended across ADS. Isn't that also a condition? You need both Compton and the Broglie wavelength, much smaller than ADS, right?
Well, I guess, well, actually, like, yeah, in this particular context, I don't think it's necessary, but I think you can explicitly see it because I'm going to do the subtle point analysis now. So probably, like, if you still have a question, you can ask later. Okay. All right. So let's discuss that. All right. So let's discuss the subtle point analysis if there's no other question. So now let's, for now, assume that this is correct. And then try to derive the map between ZZ bar, the cross ratio, to the Mandelstam variable. And that is basically that can be done in a simple subtle point analysis. So the picture that I said is that, like, there are some particle which moves along the geodesics, and then they meet at a point. So we are supposed to compute like this kind of diagram. And the point that I want to make is that, so these are basically bulk to boundary propagator using what's called embedding formalism. I guess you guys are familiar with. Let's call this point X and then boundary point P1. So this bulk to boundary propagator takes this form. Okay? So now what we are supposed to do is to do the integral over P1.x delta P2.x delta and then P3.x delta and then P4.x delta. Okay? Yes, so I'm going to, yes. So yeah, I'm going to show that like a subtle, well, it's kind of almost obvious, but like this integral in the large delta limit can be approximated by the saddle point. That's the only thing I wanted to explain. Okay, so as I already explained, replied to Slava. Yes?
Can you just explain what these variables mean?
Yeah, okay, so these P's are kind of like you embed, sorry, so what's the, so you can embed AdS.
Oh, these are the vectors in
Yeah.
the higher dimensional space?
The factors.
The vectors?
Yeah, these are
Okay.
vectors in higher
Thank
dimensional
you.
space, yes. Yeah, it's what's called embedding space. Right, and then P's are like the same kind of embedding space which describe the boundary of AdS, okay? And now, we just don't want to do the saddle point analysis of X, because obviously, when delta is all large, it looks like it's going, there is a nice saddle point, and the saddle point action is basically given by, so let me just slightly generalize, so that different operator carries different conformal dimension. So this is obviously the saddle point action, but in addition, because in order to take into account this constraint of X, I will also going to put Lagrange multiplier, okay? And then now, what we need to do is to just solve the saddle point equation. And if you take a variation of this equation by X, then you get this equation. Okay? And now, by contracting this equation, so this, I think this is easy to derive. By contracting this equation, so remember that P and X are vectors, and by contracting this equation with X, you can actually immediately determine lambda, what lambda is at the saddle point, which is basically given by minus 1/2 times sum over dimension with operators, okay? And once you determine the lambda, then you can plug that lambda in to the saddle point equation. And now, saddle point equation takes this form, which is delta I times pi divided by pi dot x plus x is 0. Okay? Yeah, this is a very simple saddle point analysis. But now, there is a nice thing happening here. This looks a bit like a momentum conservation. And it is indeed, like you can actually interpret it as some kind of momentum conservation. So for that, let me just denote this object. This is a vector, ki. Okay? And so now, the one important property of ki is that ki dot ki. So ki, let me just remind you that ki is a delta I times pi divided by pi dot x plus x. Ki dot ki is basically proportional to delta, is proportional to mass square. So this you can actually see explicitly. And yeah, delta square, yeah, sorry. And furthermore, if you consider dot product of x and ki, this is 0 because x dot x is 1 minus 1. This basically means that this ki is a tangent vector of AdS space. So you can actually think of it as really like some kind of momenta of AdS space, in AdS space. More precisely, it basically measures the moment of the particle measured at this point. So for this particle, there's some momentum here, and then that is a ki. Okay? All right, so now, but we still need to solve for x, although we only solved for lambda, but we still need to solve for x. And to really solve for x, let's introduce this quantity, sigma ij, and which is basically Mandelstam-like variable made out of these ki. And so this take this form, pi dot x, pj dot x, And in terms of ki, this is just delta I, delta j, divided by sum over k, delta k, 1 minus ki, kj, I guess. Okay. And and using this quantity, you can actually, so this quantity I just introduced, I still haven't determined what x's are. But the nice thing about this quantity is that this quantity satisfies two nice equations. One is this one, sigma ij. If you sum over j, you get delta I. So this you can actually show by using basically like this equation, sum over I, ki is 0 at the saddle point. And another thing is that if you take a ratio, sigma ij, sigma ikl, sigma, then this is nothing but pi. So this is kind of like easier to see from this expression because things cancel out, things that in the denominator cancel out. So you get this combination, which is nothing but the cross ratio, conformal cross ratio of the boundary operator, because this becomes zi minus zj squared, okay? And if you count the number of equations and the number of variables, so the sigma, you can actually see that like you have enough number of equations to determine fully sigma ij, using the fact that sigma ij is symmetric with respect to I and j. For example, in the case of like a 4-point function, because sigma ij is a symmetric tensor, so you have like a 6 degrees of freedom of sigma ij. But this equation can be defined for each I, which means that there are 4 of this equation. And then we all know that in the case of 4-point function, there are 2 independent cross ratios. So you have 2 equations from here, which means that together you can fully determine sigma ij. Okay? In AdS2, I think, let's see. I think different sigmas are related in that case. And in the case of like n equal 4, the 4-point function, and furthermore, if you impose all the dimension of the external operator to be the same, you can actually explicitly solve this equation for sigma. And then using the fact that sigma can be interpreted as some kind of Mandelstam variables of the flat space amplitudes, that allows you to relate the dimension. Once you fully solve the sigma, you can actually relate the conformal cross ratio in the Mandelstam variable. Right. So you solve for sigma in terms of cross ratio. And then you basically identify sigma with the Mandelstam variable.
Why is this a natural thing to do? Because I thought you were trying to find the position of the points of the boundary.
Right. So, sorry, like in the bulk.
I think an helpful comment is to say that the bulk to boundary propagator is just the exponential of the geodesic length between a boundary point and a bulk. So this computation that you're setting up is just finding in terms of boundary variables the bulk point which minimize the action.
Right. So we were like doing the integral over x, and then we were supposed to find the minimum of this integral. So like we are supposed to find the bulk point. So you fix the boundary point, and you are asking what is the bulk point x. And well, there is always a bulk point actually. So so it's slightly different from like what people call bulk point limit, and like that might be confusing. That might be a little bit confusing. Here we are talking about the Euclidean geodesics, and that's why like you can always find a point. And so naively, what you might want to do is to just determine x. But what we are doing here is that you actually don't need to determine x directly, because what we care about is the how, like basically like the map between the boundary points and the Mandelstam variable that you define here. And for that, like it's actually easier to just solve the equation for sigma ij. That's the whole point of introducing this sigma ij.
Could you just explain what the, I mean, I understand you're looking for the bulk point. Could you explain what the connection is with the Mandelstam variables? Are these like local momenta going into that point?
Yeah, it's a local momenta like measured at that point, yes.
And why should that be the thing corresponding to the asymptotic momenta when we take the flat space limit?
Right, because like essentially what happens in a flat space, taking a flat space limit is enlarging this region, and then this region becomes flat space. And in addition, there is a leg factor, which is coming from the Euclidean action with the geodesics. Yes, but so far I've done the computation in Euclidean. I found one saddle point, and then that gives you some relation. I'm going to, okay. Yeah, please ask the same question in 3 minutes. So after doing this, I get some relation between Mandelstam variables and cross ratio, and we were calling it conformal Mandelstam variable. So here I'm setting mass square to be 1 for simplicity, and in that convention, the relation between Mandelstam variables and the cross ratio is given by this. And then u is basically coming from the equation, solving the equation s plus t plus u equal 4. And what is rho? Rho is the famous bulk. Sorry, it's not this one. The radial variable, which is related to the standard cross ratio in this way. Okay. And now I can probably answer Sylvia's question. As you can see, in the Euclidean domain, s is smaller than 4 because square root of rho bar is always like positive. And then t is also smaller than 4. And you can also show that the u is also, like absolute value of u is also smaller than 4. So in the Euclidean kinematics in CFT, corresponds to this kinematics, which is not the scattering kinematics. And if you want to go to the Euclidean kinematics, you need to do the analytic continuation, like and go to the Lorentzian kinematics. So this is how you kind of like naturally recover Lorentzian kinematics. Okay, sorry. And so for the sake of, so let's also introduce mass as well, because probably at some point we are going to discuss the massless limit as well. All right, so now, so this basically gave you the map between the Mandelstam variables and cross ratios, and using this, we can formulate what we call the amplitude conjecture, which we,
Meaning that you work in Euclidean and you want us to believe that in fact this is going to be relevant to the. So in the old days, people tried to do something more physical, where they would start directly in Lorentzian AdS, try to scatter some wave packets. So you leapfrog all that analysis through this very smart computation, but in the end of the day, what is the relation between this old approach and this new approach?
So, for example, there, in what's Slava called old approach, there is a proposal, concrete proposal relating mailing amplitudes and effluent space amplitudes, based on the argument of preparing a wave packet. That was a kind of a more refined version of this old proposal by Joan and others, and you can relate that with this. So basic idea is that here we are working in a position space. So write the position space correlator as an integral of the mailing amplitude. And it turns out that in this a large radius limit, this integral of the mailing variable actually has a saddle point. And if you evaluate that mailing amplitude at the saddle point, you basically recover this relation.
Yeah, so in the original derivation of the flat space limit formula, he checked it for contact interactions only and then stated that because of effective field theories reducing everything down to contact interactions, ultimately this is a general proof. Does your argument that you've made now bypass that, or you still need to say that so that this, these 4 bulk boundary propagators going to a single point is enough?
Okay, so yeah, so this argument is not at all rigorous, and then what I'm going to discuss now is that there are cases in which this doesn't work, but there are some kinematic region in which this also works, and then that region, if you're in that region, it also works for exchange or more complex other diagrams as well. So let me just state a conjecture first now. So now the conjecture is that you take 4-point function and then subtract the kind of a free part, which is GFF, generalized free field. And this is just the equivalent to focusing on the connected part. And then divide by this contact witten diagram. This basically takes care of the leg factor that I was talking about. And if you take the limit, large R, the conjecture is that this is equal to the amplitudes, amplitude mean this part, a 1 plus IT in a T part. and then the relation between the Mandelstam variables and the cross ratio is this one. So that's the conjecture. So this is just removing this leg factor that I was mentioning in the beginning. It's coming from the propagator, Euclidean propagator. Okay.
So Shota, a quick question. What if your theory in the bulk is CFT and I try to blindly apply this formula? Is there any meaning to this scattering amplitude on the right-hand side and CFT scattering amplitude that people define?
So that's a good question. First of all, it's a little bit tricky, again, because it's a kind of gapless theory. But still, it's an interesting question. Yeah. I think I don't know the answer. Okay. So what should I do now? It's a 5 minutes, 10 minutes, 15 minutes? 15 minutes, okay. Okay. Okay, but yeah, but I'm not okay. But I'm gonna speed up a little bit. So let me just discuss a little bit more about kinematics using this map. So as I already said, one thing I already said, which is a Euclidean kinematics conformal field theory map to this STU 0 from 4m square. So another thing is that if you consider Lorentzian kinematics, there is in the rho bar plane, there is a branch cut starting from 0. So this is a kind of famous fact if you want to analytically continue conformal field theory correlator to Lorentzian. And this branch cut precisely maps to basically 2 particle threshold branch cut in the S-plane. So this you can actually see from the from the map that I wrote down. And Furthermore, another thing is that, like, which I already replied, which I already said in reply to Silvio. So if you want to really consider the scattering kinematics, you need to do this kind of rotation. So you don't do anything to the rho bar, you just rotate rho. So this is equivalent to going to the Lorentzian kinematics. And that basically changes the equation, basically, to this one. Yeah, so that's sorry, so you are saying that why we don't see the anomalous threshold? Well, I'm just saying that here I'm just saying that this one is mapped to this cut, but I'm not saying the existence of other singularity. I'm not saying anything about existence of other singularity.
So on the left, you really don't have any singularities for this analytic continuation. So you really have an analytic function.
Yes.
So if you conjecture that the analytic continuation of the left-hand side describes the right-hand side is true, then you're basically proving that there should be no anomalous thresholds.
Yeah, that's perfectly correct. And then that's why this, this conjecture only works in certain kinematics. And then the rest of my lecture today is to explain when and why. Okay, so now let me just briefly say like what. So this also kind of like, well, there is still a question of like whether this formula really works or not, but assuming it works, it relates some kinematics in CFT to some kinematics in scattering amplitudes. And then let's first ask like what is the usual OP limit when rho bar is 0. That basically gets mapped to S is near 4m squared, and then T and U are near 0. So it's kind of like a near threshold static particle. And Regge limit, you can also, I'm not going to write the expression, but the Regge limit is basically Regge limit. The conformal Regge limit is nicely mapped to the Regge limit of the amplitude. And then let's also talk about the bulk point limit. So the bulk point limit is basically rho going to e2 minus I pi minus epsilon times e to I theta. And then rho bar is also e2 minus I pi minus epsilon e to minus I theta. So this is the bulk point limit. And if you just plug that in to the original equation, so because this is all like a rho and a rho bar now becomes minus 1, basically the denominator...
Maybe it's a little bit strong assumption to assume that everyone in the room actually has a memory about why all these manipulations with rho have anything to do with physics.
This bulk point limit, sorry?
Yeah, for example, what is bulk point limit? Why this thing? Why the analytication of rho? Why this maps you to good kinematics?
Okay. That's a good point.
I certainly I've seen these things, but if this is going to be important for the rest of the lecture, then this is where I'm going to decouple. Let's put it this way.
Okay. So what is rho? So normally in CFT, we put three operators, 0, 1, and infinity, and the second operator put ZZ bar. So this is a kind of canonical frame in which you define the cross ratio. But there is a nicer frame, which was discussed by Slava. And so this is a ZZ bar frame, in which you put operator 1 and 2 at 1, 0. So let's pick 2D plane. And operator, I forgot it was, it was 3 and 4, I guess. Operator 3 and 4 here. And then put the operator 1 and 2 in a symmetric way. So here, like operator 1 is sitting at, rho and rho bar in the 2D plane. And then the 2 is minus rho and minus rho bar. So this variable is much more suitable for analyzing the convergence of OP and conformal block expansion. But you can also kind of like view this in a radial quantization. Then basically, okay. So let's imagine drawing this on a sphere. So here we have a plane, and then now I'm going to draw it on a sphere. Okay. So this origin becomes north pole, sorry, south pole, and the infinity becomes north pole. All right. And then this 1, 0, and a 0, minus 1, 0 is kind of sitting here. And then rho bar is somewhere sitting here. So you have like 1 and 2 here, and then 3 and 4 here. Okay? And now, in order to go to this, I basically need, so this is like introducing imaginary radial direction, right, in the rho coordinate. So it's basically, that means that like when you separate 1 and 2 and 3 and 4 by kind of like putting some kind of like a Lorentzian cylinder in the radial quantization. And after doing this, it looks more like a scattering kinematics because 1 and 2 sits in the past and the 3, 4, and 4 sit in the future. So this is why, in some sense, like why intuitively this is related to the scattering kinematics, physical scattering kinematics. And furthermore, so this in particular, this bulk point limit basically corresponds to you are inserting like a Lorentzian cylinder of size pi, and then inserting operator 1 and here near this edge of the cylinder, and then 3 and 4 near the top edge of the cylinder. And if you put it like this, like approach the operator like this is called a bulk point limit. And the reason why this is special is that like if you have some like effective field theory description in AdS, if the operator approaches here, there is a point in the bulk which are light-like separated from every point on the boundary. So that's why this is a kind of like this produces some singularity in the correlation function, which you wouldn't expect from the boundary correlation function. And also, from this picture, you can already see that like here now, the particles are really traveling along the light ray, which means that these particles are actually very energetically fast. And you can actually see it in this map, because if you do this, and you can actually see that like S going to infinity, and the scattering angle theta is finite. So this is just like a fixed angle, high energy scattering. Okay. All right. Physical.
So let's say S and T are both larger than 4m squared.
Right. S and T are both larger than 4 squared.
Where the double discontinuity of the amplitude is.
Yeah. I don't remember where it corresponds to. I think I once thought about it, but I don't remember it. So another thing that I wanted to mention is that like you can also study what's called double light cone limit. Double light cone limit basically corresponds to like us sending this ZZ bar somewhere here. And that, if you do this relation, if you just naively translate what it corresponds to in the Mandelson variable, this basically corresponds to this limit in which like both epsilon and eta are like this. So this is a consequence of the using the map, but I actually don't know like what is the significance of this regime in the scattering amplitudes. But given that there is like a double light cone limit, was very useful in analyzing correlation functions and understanding the large spin spectrum. There might be some use in this kinematic region, but I honestly don't know like whether people analyze or like what is the physical meaning of this limit from the in the context of scattering amplitude. Okay. So how much time do I have? Or in 5 minutes, I guess. Right. So yeah, now let's then in the remaining 5 minutes, let's just start introducing or start pointing out the subtlety about this formula. Dynamic. So far I was just doing like a simple kinematic analysis, mapping Mandelstam variables to conformal cross ratio. But you should ask like whether this formula really works, because as many people pointed out, I just derive it using some Euclidean subtle point analysis. So for example, the simplest thing I can do is that I just take some AdS written diagram, for example, exchange diagram, and then apply our formula, and then can we get expected answer of the exchange of particle with mass mu. And in fact, it actually doesn't work. Well, sometimes work, but sometimes not. So it works like this. So if you are in some domain, you actually get just infinity. And if you are in other, like if you're not in that domain D, which we call bad region, you get the right answer. So what is the bad region? So the bad region, in terms of like a Mandelstam variable S, so I using this, it's basically this big circle around this 4m square point, and the radius of the circle is given by 4m square minus mu square. And so two things I should point out is that bad region is big. For light exchange, light particle exchange. And another thing is that no bad region if mu square is larger than 4m squared, because it basically shrinks. Okay? At least no bad region on the first sheet. And furthermore, like you can also see that the high energy is always safe, at least in this analysis. Like a high energy, which is like a S going to infinity, which corresponds to bulk point limit, is also safe. And I'm going to explain why, where this is coming from in the next lecture. But basically, let me just already give you a preview. Basically, the reason why it doesn't work is that there is some other subtle point in which looks like this. So this, like a bad region coming from the existence of the other subtle point, in which you basically two particles immediately annihilate and then emit some particle of mu, and this particle of mu with mass mu travel along the long distance in AdS. And of course, like this doesn't look like this knows about AdS curvature, and it doesn't look like a flat space amplitude. So when this contributes, this flat space limit has a problem, and that is a kind of, and I'm going to show it a bit more explicitly in the next lecture. Yeah, so it has two bulk points in this case, yeah. And yeah, so in the next lecture, like I'm going to give a bit more detail about this, and then like also explain like because this is a very perturbative picture, and explain like what people did to define this procedure also at the non-perturbative level.
questions?
Shota, can you comment on what's the expectation for the bad region in the non-perturbative case?
Right. So I think in the non-perturbative case, like basically this with mu equals 0. And also the similar thing around the T-channel cut.
So you wrote this formula as a limit when R goes to infinity. R is dimensionful. What is the dimensionless quantity that goes to infinity?
That's delta. All the operators' dimensions becomes infinity.
Okay. And in terms of the kinematics, in terms of the x's in the correlation function, then there's no...
That you don't need to take the limit.
Okay.
So that's slightly different from like this bulk point limit and extracting masses scattering amplitudes.
I see. And one other question: how does spin work in this case, in this limit? So if I consider operators with spin and corresponding particles with spin, how does that work?
Right. So that's an interesting question. I would expect like basically operator with spin become just a particle with spin, but I don't think that the details have been worked out.
Regarding the double Lect1 limiting, you said that it's not yet clear what's in the flat limit, but well, one can draw the diagram, the example that you did with the conformal Regge theory, and say, I have light ray operators on one side and with a match on the other side. Well, this might be just my ignorance, but what do you match to the double twist families on the other side? Is it clear?
I guess double twist family is basically should be two particle states.
Yeah, so this should be a limit where...
Yeah, somehow it's better, it should be a nice limit to extract some large spin two particle state or large spin two particle density, but...
Not clear.
Yeah, but I just don't know, or I don't know any literature which uses this limit in the S-matrix bootstrap.
Yeah, thank you.
Thanks. I was wondering, could you just say maybe a little bit about the motivation of the new method versus the old methods, what it is you want to achieve that the old methods didn't achieve? So, like the old methods, they didn't have these bad regions. Is the idea that the new method is simpler, or it can do more regions of, you know,
right, so
Mendelssohn variables or something?
So I guess like so I think that the advantage is in the non-perturbative approach, which was explored especially by Bolt and Shan. The new method is basically I would call like position space method, and the reason why we preferred position space is that we know more about non-perturbative properties of correlation function in position space. Whereas like if we needed to go to the Mellin amplitudes, we first need to like establish the properties in the Mellin amplitudes, some of which are already established, but like still like much less is known as compared to the position space correlators.
But what about, you can also go back to a previous step. You can also go back to a previous step. In the old methods were trying to basically take integrals where you set up these wave packets. You know, I mean, is it that's more complicated and these formulas are nicer, or are you trying to extend the regime of validity compared to that?
Right. So also there, like I think the difficulty is that like if you need to do the integrated correlators, like the analysis of analytic property is much more complicated.
So just to make sure, this anomalous threshold would be in the bad region also. So this would be...
Yeah.
Yeah. It would be at the edge. These points are always at the edge of the body.
Right, yeah, could be.
Any other questions? All right, I think you want to, let's thank Shota again first.
Yes, I just want to make a small announcement for this afternoon. It will be free, and the idea is to meet at the Italian consulate I want to say some words to demystify this event reception that you are going to have. So during the year, there have been many scientific events at the Italian consulate because of the proposal that Italy is going to put forward the new gravitational wave accelerator called Einstein telescope. So, detector called Einstein telescope. So during this year, there are many events, and then in one of these, I just came about the possibility to host the reception of the Bootstrap in the consulate. So it's a normal thing that is usually done for other events, so we are just happy that we've been invited to the consulate. There will be some security process that is standard. So since you are many, they asked me to just tell you in advance that you have to show the ID, the one that you give me for the list. And then the idea is to meet at 6:30, do the process, and then we will start the symposiums actually in the banquet hall. There will be also blackboards, so I think it's going to be a nice opportunity to stay all together, chat about physics. There will be the receptions. People around will be serving the buffet. So I hope everybody will enjoy the event, and see you in the afternoon.